If a company, for example, wanted to recycle spent nuclear fuel and reuse that fuel for future nuclear fuel applications, they have to get rid of a lot of the nasty byproducts. And some of those nasty byproducts are rare earth elements. Rare earth elements have been difficult to separate from spent nuclear fuel because they have very similar crystal chemistry. They're just really difficult to isolate. And so what we found is that through a multi-step process, that we can absorb just specific rare earth elements using minerals and leaving everything else behind. I'm really interested in the group of minerals that are called zeolites and zeolite-like materials, and having the greatest diversity of those available to me makes my research projects a little bit easier to accomplish. A lot of my work is on separation of heavy metals and gases from streams. I'm interested in absorbing radioactive waste from groundwater, and these minerals are really good at absorbing just the radioactive waste component and leaving behind everything else. Some of these things can be used for pharmaceuticals. So, for example, if somebody ingests huge amounts of heavy metals, then these minerals can then be ingested by the human being and then go through your bloodstream and scavenge out the heavy metals. They're so selective of just absorbing the heavy metal that they leave all the other elements in the bloodstream behind and just pick up the toxic stuff from the body and rescue the people. Now the junk is just stored at the fuel generating site right now, either in a solid form or also sometimes they're stored in cooling ponds as well. So that's the way it is around the country. Is there's all this spent nuclear fuel with really no place to store them. A lot of it hasn't been recycled or treated in any way. What we do in the lab is that we take a mineral and we have a particular application in mind to identify the properties. We say we want a mineral that is good at absorbing strontium. It's a high-level waste gamma emitter. We take a mineral and we put it into a little chamber, just crush it up and put it into a little capillary, and then we start passing a strontium chloride solution over that. And then we observe in real time using Raman spectroscopy or time-resolved X-ray diffraction how that mineral changes on the molecular level. If it does change, then we've captured that process through the time-resolved work, and then we can go back and try to decipher what the mechanisms were involved in capturing that. Once we figure out how a mineral, say, absorbs lead from the groundwater, and we understand the molecular mechanisms involved and identify what the atomic arrangement is to generate those molecular mechanisms, then we can go back to the collection and go back to our database and say, okay, what other minerals share similar properties as this one? And do those also have these highly functional aspects to them? A lot of fundamental research and trying to figure out how these radioactive wastes are absorbed by the minerals. And then hopefully that can tell us something how the minerals behave that can then be used for scale up industrial applications for large environmental disasters. Rare earth elements are really good for phosphor imaging, really good for fluorescence type work. And so if you can absorb the rare earth elements out of the waste, then that zeolite or that mineral then has a functional property as well. So then it could be used for other applications. What's left over is usable, or it could be then treated again. So using a different mineral to absorb a different byproduct as well. So there's lots of applications. Some of the discoveries that have been made in this lab, I believe, have gone on to industrial scale. Now, they don't tell me that they're using that particular stuff, but from what I've seen come out from other companies is that they are using these sorts of tricks that we've learned in this lab to develop their materials. So the types of donations that I'm interested in getting are of really rare specimens that may be only a few centimeters across or even smaller, just to have a really good diversity of specimens, mineral specimens in the collection. I know it feels good that what you're doing is actually being applied to real world applications, and that's what keeps us going. That's what keeps us encouraged that maybe 2 or 3 years from now we find something new, and then that is eventually being used for other applications.